Thanks for the great intro, Amir. I'm really happy to be here to talk about our recent work on 5G edge computing, which enables you to run some of your low latency real-time application by using this emerging 5G, the edge computing infrastructure. So this is a joint work with my PhD student, Xiao Zhang. So just to quick primer on what's the 5G multi-access edge computing, or MEC. So if you look at how the current 5G network is deployed today, we have lots of user devices such as your smartphone, your car, and robots. And there's 5G cellular networks, which is operated by AT&T or Verizon. And then there's an edge computing facility, which is operated by the cloud operator, typically with AWS or Azure. So this MEC vision, like a multi-access edge computing vision, allows you to offload some of your latency critical and compute intensive tasks to this edge computing device, because most of your device is has a lightweight compute power. So by offloading some of your compute-heavy operations, tasks such as video transcoding and object detection from your live video, you can actually enable these low latency applications on this edge computing architecture. So typically, this low latency application consists of, has this request response pattern, where the client send the request, such as send a video frame, a set of video frames, and then on the edge over the 5G network, and then at the edge server, there's a processing happening, such as video transcoding or object detection. And then this edge server will send a response back to the client, such as the result of the object detection or transcoded video to multiple devices. So typically, these applications has latency requirement, or service level objective requirement, such as hundreds milliseconds for augmented reality, or 150 milliseconds for video conferencing. So which are very critical for quality of experience for end user. Then the natural question is, does the current Mac deployment provide such a low latency guarantee? So that's why we did some measurement study on real 5G MEC deployment on 3 different cities across US, China, and Korea. And we also use different Mac offerings from AWS and Tencent. And we run the real applications on this the deployment. And then we measure the end-to-end latency and see whether the current offerings provide the end-to-end latency guarantee. So result is quite surprising. So today's offering actually shows a very high tail latency, or very a variable the latency, end-to-end latency. So in this figure, you can see this red line is a SLO requirement for a specific application we are running, the Smart Stadium video transcoding application. And you can see here all 3 cities shows very long tail latency. So this is a CDF graph, the CDF graph of the end-to-end latency. And you can see the more than 30% of your request will just miss the deadline, the SLO requirement deadline. And why this happened? We actually run the same measurement, but even without compute contention, like edge side resource contention. And you can see here, even without any contention, many of these requests will miss the deadline. And also, when you do the same measurement on some busy network busy times, such as 2 p.m., then just all of your requests will miss the deadline. So yeah. So here, there's 2 cases. One is Dallas, just say 2 a.m., for example, and this is Dallas busy time. So when you try to run low latency application during the busy time, then just all of your requests will miss the deadline. Yeah. This is the same network, but different time. So this is what we observed. So this means the 5G's wireless resource, the wireless contention causes this high tail latency. That's the reason number 1, root cause number 1. And even we break down this latency part, wireless latency part, into uplink latency and downlink latency. So uplink means from client to edge server, and downlink means like edge server to client. And you can see the downlink is pretty stable. That shows a pretty stable latency regardless of your request or response size. But you can see here the uplink latency varies a lot. Also depending on your request size. So this means the uplink contention is a critical factor of your latency variability. And then another reason we found is resource contention on the edge server side. So we varies like CPU contention or like GPU contention level on the edge server and measure the same, run the same application and measure the end-to-end latency. And you can see here, as we increase the load, the compute load on the edge server, the more number of requests will miss the deadline, yes. That's a good question. In cellular deployment, what operators do is actually they limit they allocate more resource, more bandwidth to downlink. Yeah. So that's another one reason why uplink has a more higher the variability for a given the same amount of resource contention, right? Good point. So as we saw, this SLO unaware resource scheduling is the key issue for all this latency variability problem. So in this MEC architecture, there are two types of resource scheduling happening. One is resource scheduling, the wireless scheduling happened at the radio network, cellular network. And the second thing is the edge scheduling, edge compute resource scheduling, which could be like CPU or GPU scheduling at the edge. So today's existing resource scheduler consider fairness across multiple requests or multiple applications, or the resource utilization, like a spectrum utilization in case of wireless network, but not application SLO requirement. So these are examples of the resource scheduling algorithm used in the RAN and the CPU side, the edge server side. So our vision is to solve this problem. Our vision is to develop a practical and SLO-aware resource management framework for 5G MEC. So our goal is to improve SLO satisfaction rate without any infrastructure or application level modification. So we don't touch any infrastructure stack or application. So this is a kind of current architecture. And we let the RAN get the SLO information of each application through the standard interface. So we leverage the existing interface between the user client and the 5G network. And then once we have that information at the RAN, the client just sends the request as is, like previously. And then our approach is we let the RAN and the edge server estimate the deadline or remaining time budget of each request, and then use that information for deadline-aware resource scheduling. So for that, on the RAN side, we get the information such as the request start time to compute the remaining time budget, and on the edge side, we need to get the network delay, both uplink and downlink network delay, and then estimated processing time of the incoming request so that we can compute or we can estimate the remaining time budget. And then we are going to use that for deadline-aware scheduling. So then the question is, this looks very simple, but the question is it really achievable vision? So there are definitely several practical challenges to realize this vision. One is for this request start time estimation. The problem is the RAN, if you know a little bit about the physical layer or MAC layer processing, The RAN only has access to signal level information. It does not know anything about application request or any upper level information. It doesn't have application semantic. So because of that limitation, and also another, the key constraint on the RAN side is it has very tight timing requirement for physical layer processing, such as for every 500 microsecond, it needs to process, or it needs to make a scheduling decision for every 500 microsecond. So there's no time to receive a construct a packet and parse the packet and get the application level information. That's a challenge one. And then the next challenge is on the edge side, how to estimate the network delay for both uplink and downlink. Because the edge server does not have any access to the RAN or what has happened on the RAN and what will happen at the RAN. So it doesn't have such an information. So it's very hard to estimate the network delay. And the last challenge is estimating processing time under like a varying workload, the patterns. So our work basically tried to address each of these challenges and to realize our vision of the SLO-aware resource, the management framework. So our key insight to address all of these challenges is we actually observed we can exploit natural signals and properties that already exist in this MEC architecture. So for example, we observed that there is a standard 5G protocol's control signal between the client device and the RAN. And then we can actually leverage this control signal pattern to identify the request start point. So that's the one example. And to measure the network delay, we can actually exploit the stability of 5G downlink. So if you remember from the previous slide, we saw while the uplink latency is varies a lot, but the downlink is very stable. So we can leverage that property of this 5G network to estimate the network delay. And lastly, for processing time estimation, we can leverage the request and response pattern of this MEC application. So I'm going to dive into detail of each of these ideas. So for this, the request start time estimation at the RAN, what we leverage is the control signal between the user client device and the RAN base station. So periodically, the user device will send this control signal called BSR, buffer status report, which reports how many bytes are buffered in its buffer, local queue or buffer. So if there's nothing to send, then BSR reports 0 byte. And when the client tries to send something, the application level, the application tries to send something, then the 5G modem, 5G stack will send the SR information. The SR means a scheduling request, the control message. And then the RAN allocate some resource. So this is where the actual resource allocation is happening. And then once it allocates the resource, then either send the uplink RAN message to the client, and then the user device can send the data with additional BSR report. So here, once we receive the BSR, which is equals to, not equal, the greater than 0, and the actual data, then we can detect the request. And also, when the RAN receive a SR message, then that's the point where actual request has started. So on the RAN side, without any application level packet parsing, we can actually detect the request start time just using this 5G, the control signal packet. So by the way, these blue messages are not introduced by our protocol or our system. This is existing control signal from the 5G standard. And then once we get that request start time information, that timestamp, we can actually compute the time budget, the remaining time budget from the RAN side by computing this the SLO and the difference between SLO and the start time information. So this is a quick comparison of like how the accuracy of our like start time or the request detection mechanism. So this graph shows the P99 error. So this is a very like tail error. And the 2T and ARMA are kind of existing mechanisms that requires the coordination between the edge server and the RAN base station. So you can see here our method, SMAC, shows very like low error, which means like a very high accuracy compared to other existing approaches, which requires like infrastructure changes, basically. But in our case, we don't require any infrastructure change because we rely on existing 5G protocol signal. So using that information, given the deadline information, remaining time budget information, we can actually do some deadline. We can conduct the deadline-aware wireless scheduling. So there are two types of request or application traffic we need to deal with at the RAN side. One is latency critical information request, which has an SLO requirement, such as like AR, VR, and this type of low latency application. And there's another best effort request, which does not have any like SLO, like file transfer would be a good example. File transfer or web browsing would be a good example. So among LC requests, low latency critical request, we prioritize request with a smaller or smallest remaining time, like remaining time budget. And then between LC and best effort request, we prioritize LC request because that's our goal, to accelerate LC application. And to avoid starvation of best effort request, because this is also important because under the same 5G network, there could be multiple users. Someone uses a latency critical application, the other uses just a file transfer application. So we should not starve the best efforts, the users. So we prioritize we prioritize BE, the best effort, the traffic, which hasn't been served for a while. So using such a prioritization, we avoid the starvation for these best effort applications as well. So we implemented this new scheduling and also new like request detection algorithm as part of open source, the 5G implementation, and we show it works in practice. And this can be ported to other the 5G stack as well.